Ever stop to think about the invisible rules that keep our world from flying off the rails? I mean, from the simple thermostat in your house to these massive, complex industrial plants, there's a hidden logic at work. It's a system of self-correction that honestly prevents total chaos. So today, we're going to pull back that curtain and take a look at that very logic. All right, so here's our game plan. We're going to start with the fundamental problem that all these systems are trying to solve. Then we'll break down the really elegant solution, which is known as the feedback loop. We'll get to peek inside the brain of the operation, the controller itself, and we'll meet its three main personalities. And finally, we'll see why this stuff actually matters in, well, pretty much every part of our modern lives. So yeah, it all kicks off with this universal challenge. How do you keep a system stable? How do you make sure something stays at the exact right temperature, or the right pressure, or the right speed, especially when the world is constantly trying to mess it up? Let's start with the classic example, right? Your thermostat. It seems so simple, but it's solving this exact problem day in and day out. And it's not magic. It's this brilliant piece of engineering that is constantly asking one question. Are we where we're supposed to be? And if the answer is no, it takes action. That simple idea is the key to everything we're about to get into. And this visual, it says it all. Over on the left, you've got a simple process. You put something in, you get something out. But it's totally vulnerable to any kind of disturbance. It's just unstable. But on the right, you have that same exact process, only now it's wrapped in what we call a feedback loop. And suddenly it's stable, it's predictable, and it corrects itself. So let's actually break down this blueprint for control. The feedback loop is really the hero of our story today. It's this simple, repeatable pattern that allows a system to regulate itself, completely automatically. Okay, so this whole system can be broken down into four key parts. Let's use our thermostat to make sense of it. The process. That's just the air temperature in your room. The measuring device is the little thermometer inside the thermostat that's checking that temperature. The controller is the circuit inside that compares what it's measuring to the temperature you actually want. And finally, the final control element. That's the switch that physically turns your furnace or your air conditioning on or off. See? It's a closed loop. Now, at the very heart of this loop is a single, vital piece of information, the error, often shown with the Greek letter epsilon. And listen, this isn't an error like a mistake. It's the most important piece of data in the whole system. If you set your thermostat to 72 degrees, but it's only 70 in the room, the error is 2 degrees. The entire purpose, the whole job of the controller, is to take actions that will make that error disappear. Okay, so now we're going to zoom in on the most important box in that whole diagram, the controller. This is where all the decisions get made. It really is the brains of the whole operation. Its job is, beautifully simple, but also incredibly powerful. It takes in one number, that error signal we just talked about, and based on its programming, it calculates a response. It then sends out a command, what we call an actuating signal, telling the system what to do next. It decides how much to open a valve or how hard to turn on the heat, all with that single-minded goal of getting the error back to zero. But here's the thing. How a controller decides to react isn't always the same. There are different strategies, or as I like to think of them, different personalities that determine how it responds to any given error. So let's meet the three main characters in the world of control theory: the proportional integral, and the proportional integral derivative controllers. You'll just hear them called P, PI, and PID. First up is the P controller. And this one's the most straightforward personality of the bunch. Its logic is simple. The bigger the error, the bigger its response. Just think of it like this. The further you are from your goal, the harder you push to get back. So a tiny error gets a tiny correction, a huge error gets a huge correction. Make sense, right? And you can literally see that logic right here as a straight line. As the error on the horizontal axis gets bigger, the corrective action from the controller on the vertical axis goes up in direct proportion. It's simple, it's effective, but it does have its limits. And that brings us to the P controller, which is a bit smarter. It has that immediate reaction of the P controller, but it adds a new trick: memory. The integral part looks at the error over time. It basically says, hey, this small error has been sticking around for a while now. I need to ramp up my efforts and finally get rid of it. Check out what happens here. When an error pops up at time 0, the controller immediately makes that proportional jump in its output. But then, as long as that error sticks around, the controller's output just keeps climbing, steadily and steadily. That's the integral action at work, trying to eliminate even the most stubborn, lingering errors. But that powerful memory? It can also be a pretty big weakness. It can lead to a really common problem in control systems called integral wind-up. So imagine the controller is screaming for a change, but it can't happen. Maybe a valve is already fully open and can't go any further. The integral part, the memory, doesn't know this. It just keeps demanding more and more power. It's kind of like flooring the accelerator while your car is stuck in park. It winds itself all the way up to its maximum output. So when the system can finally respond again, that pent-up energy gets unleashed all at once, causing a huge overshoot. And that brings us to the gold standard, the PID controller. It has the P for present action and the I for past memory, but it adds a D for derivative, which basically gives it a crystal ball. It looks at how fast the error is changing, and that allows it to anticipate the future. It's the part that hits the brakes before you get to the stop sign, so you don't fly right past it. This ability to anticipate is incredibly powerful. It makes the whole system more stable. It fights back against that wind-up problem from the integral part, and it helps the system lock onto its target much, much faster. But the real art is in what's called tuning the controller, finding the perfect balance between T, I, and D. Too much P makes it jerky, too much I causes that overshoot, and too much D can make it oversensitive to noise. Getting that balance just right is what separates a good control system from a great one. So we've met our three personalities: the reactive P, the remembering PI, and the predictive PID. Now let's zoom back out and ask the big question: why is any of this so important? Because it all comes back to this one fundamental question from our source material. This is the core challenge of modern engineering. In a world that's filled with unpredictable changes, how do we build systems that actually behave the way we want them to? The answer is feedback control. And this logic is absolutely everywhere, just running silently in the background of our entire world. We see it here in diagrams showing feedback loops controlling the liquid level in a tank, the temperature in a heat exchanger, the pressure in a vessel, and the chemical composition in a blending system. Our entire industrial infrastructure, from power plants to refineries, runs on this principle. And that, right there, is the key takeaway. Without this logic, our world would be unpredictable, it would be unstable, and it would be wildly inefficient. But with it, we can create systems that are stable, self-correcting, and unbelievably precise. It is truly one of the most powerful and elegant ideas in all of engineering. So the next time your air conditioner kicks on, or you use cruise control in your car, you'll know the unseen logic that's at work. And that leaves us with a final thought. Now that you can see the pattern, where else do you see feedback loops controlling your world?